All right, so we are going to look at some different growth tables, patterns of growth. So far, we've looked at several types of sequences. We've looked at linear growth and exponential growth. We've looked at tables and graphs, and we're going to compare patterns of growth rates to each other. It'll also help with writing equations for exponential sequences in the next lesson. So your task, represent these three sequences on a graph. You've been provided with both blank versions of the graph and completed versions of the graph that you can look at. Use a different color for each sequence. Although the graph is discrete, connect the points so you can see the patterns more easily. Meaning, this should be a graph of points because it is a sequence. However, they're suggesting that you connect the points so that you can see either that it's linear or that it's curved and how the curve looks. Sequence A, so we are specifically looking at the first one here. It says, how do the inputs n of the sequence increase? So 1, 2, 3, 4, they increase by 1. Do the outputs, t of n, of the sequence increase by a clear pattern? So we're looking to see if there is either a repeated addition or repeated multiplication. So first I'm going to look for addition. 27 plus 27 will give me 54. 54 plus 27 will give me 81. 81 plus 27 will give me 108. So yes, and it is a repeating addition. So repeated addition, and it is plus 27. How does the sequence grow? Well, if it's repeated addition, we know that it is linear. Is the rate of change constant or changing? It is constant, also because it is linear. How? Draw growth triangles to help answer this question. Well, if we look at our graph, we will be able to see that sequence A would be a straight line, and it would have a rise of 27 for every run of 1. So every time you would go up 27, you'd go right 1. Up 27, right 1. Because n is going up by 1s, your output is going up by 27. If we knew a specific term, how would we determine the next term? For example, if we knew the 10th term, could we determine the 11th? Well, we know that the pattern is repeated addition, so we would just add 27 to the previous term. And which family of functions best models the sequence? Well, since it is repeated addition, it would be arithmetic. And determine the equation. So they've left this open. Determine the equation. If it said explicit, we would go with y equals 27x. Repeated addition, our slope is 27. If we went back to the 0th term, it would be 0, so we'd have plus 0. If they asked for the recursive, we could say in order to get the next term, we would do previous term plus 27, and that term 1 is also, in fact, 27. So we could do either. We could do explicit, which would just be the y equals 27x, or, because it's a sequence, t of n equals 27n, the y equals 27x, that's going to work on a yx graph. T of n equals 27n, specific because this is a sequence. And if you look at the graph that was provided, it was given n on the x-axis and t of n on the y-axis. Sequence B. How do the inputs n of the sequence increase? So 1, 2, 3, 4, so they are just plus 1. Do the outputs have is the sequence increased by a clear pattern? So let's see, 9 plus 27, 36 plus 45, 81 plus 63. Now, some people would jump to that and say no. It's actually a yes. 27 is actually 9 times 3, and then 45 is actually 9 times 5, and then 63 is actually 9 times 7. So we are actually increasing by every other multiple of 9. So the next one would be plus 9 times 9, or plus 81. So the next one would be 225. So is it increasing by a clear pattern? Yes. It's increasing by every other multiple of 9. How does the sequence grow, linear or nonlinear? Well, because it's not a constant addition and it's also not a constant multiplication, we would say nonlinear. Is the rate of change constant or changing? It is changing. If we knew a specific term, how could we determine the next term? For example, if we knew the 10th term, could we determine the 11th? We would have to add the next odd multiple of 9 as the previous. Which family of functions best models the sequence? It's a neither. It would have to be repeated multiplication to be geometric, so we would say neither. Now, something we have not already done are we have not already looked at writing equations for this type of a table. I can tell you that there is one, and we can write it just for the sake of being able to look at it. It is T of n equals 3 times n squared. Now, that comes from the fact that all of the 9s are also made up of 3s. The n squared has to do with the input. So 1 squared is 1 times 3. And then 2 squared is 9 times 3 is 27. So there's actually got to be more to it than that. 3 times n squared. I'm going to have to look at that one again. 2 squared is 4. 4 times 3. 3 squared is 9. Oh, so that's actually got to be 9 n squared. All right. Right? Because 3 squared would be 9, and 9 times 9 would be 81. Okay, good. Glad I said that out loud. All right, next one. Sequence C. How do the inputs in sequence C increase? It is an increase of +1, same as all the rest. Do the outputs of the sequence increase by a clear pattern? This one's a yes. When we look at it, 6, and then it doubles to 12, and then it doubles to 24, and then it doubles to 48. So it is doubling. So we would say yes, it is doubling. You could say double the previous term. How does the sequence grow? Linear or nonlinear? It's definitely not a straight line because it's repeated multiplication. So it would be nonlinear. Is the rate of change constant or changing? So this one is +6, then this one is +12, then this one is +24. So the rate of change is changing. How? Draw growth triangles to help answer this question. So every time you are doubling the rise, so when you go over 1, you're going to go up 6. Well, the next time you're going to go over 1 up 12. The next time, you're going to go over 1 up 6, over 1 up 12, over 1 up 24. So your rise is changing each time. If we knew a specific term, how would we determine the next term? For example, if we knew the 10th term, could we determine the 11th? You would simply, in this case, multiply the previous term by 2. And that would make it a geometric sequence. Determine the equation. So because this one starts with 6, it's got to be like 6 times something with the 1. 6 is our first term. So when we go to write this, T of n, and no, I'm not expecting you to like memorize this today. T of n is going to be 6 times, and it's 2 to the n minus 1, because I've got to have this has to be worth 1 in order for 6 to stay 6. So 2 to the 1 minus 1 would be 2 to the 0. This whole thing, 2 to the 0, is worth 1 times 6 would still give us an output of 6. Well, if I go to the second one, 2 to the 2 minus 1 would be 2 to the first. 2 times 6 would give us 12. If I plugged in 3, 2 to the 3 minus 1 would be 2 to the second, which would be 4. 4 times 6 would be 24, and so on. So no, do not expect you to memorize that. Just want to put it out into the universe, though. And if we wanted to look at our graphs, we could, let's see here, take a look at the 3 different sequences. We have sequence A, which we knew was going to be linear, sequence B, which is the pink one, and sequence B, which is the blue one. And they are both, like we thought, they are both geometric, or they're, sorry, not geometric. They're both nonlinear. They're both curved. And sequence A is the linear one. And then, let's see, for each part below, consider how fast each of the sequences in problem 5-83 is growing by looking at the tables and the graphs. Do not make any additional computations. Instead, make conjectures or best guesses based on the tables and the graphs. If n represents the number of years and t of n represents the amount of money in your savings account, which account would you want? So your choices are sequence A, B, or C. And there are different answers depending on how long you're going to keep your money. So if you're only going to keep your money for, say, in the account for 1 to 2 years, you'd want A. For the first 2 years, A is the best option. So for 1 to 2 years, we would say A. All right. And then anything after 4, let's see. Well, 3, we can see that A and B are kind of tied. And then we would want sequence B after 4 years, or after 3 years, I should say. So sequence B after 3 years. Now, we don't have data for when sequences B and C will intersect, but they do appear to intersect at some point further on up the graph. Would you change your answer if you kept the account for many years? B looks pretty steep, so I would say B might be the steepest. B currently the steepest. So that might be our best shot, but it looks like they could intersect. We might want to zoom out on our graph, use a graphing calculator, and look at more of the graph. Obtain the lesson 531B resource page, extend the tables and the graph to n equals 7. The table for sequence B has been completed for you. Now, I actually had all of them done on the one that you have through 7, and you can see that sequence B in year 7 is the highest at 441. And we would probably want to keep going. It says, based on your extended graph, do you want to change your answer to part B? Do I want to change my answer? B looked the steepest. Eventually, we'd probably want to go to C. C will overtake B, and it happens after 8 years. So you would actually need to extend your table and your graph even further. Which grows the most? Will an exponentially growing bank account eventually contain more money than a linearly growing bank account for the same amount of initial savings, no matter how fast or how steep the rate of growth of the linear? And the answer is yes. Use the growth triangles on your graph to help you explain. Well, if you're looking at the growth, so what we're looking at here, we're talking about these growth triangles where I started to draw. This one's up 63 over, up 81 over. And then what we were looking at in the other one is this one, the blue one, we had plus 6, then plus 12, then plus 24, then plus 48, then plus 96. Then you're going to have plus 192, then you're going to have plus 384, and so on. This one is only growing by multiples, sequence B, and sequence C is growing exponentially by doubling. So growing by a multiple versus doubling is going to be slower. Sequence B is actually going to end up slower because it's growing by a multiple, whereas sequence C is going to grow faster because it is doubling. So the growth, I'm not sure where to put my answer. Use the growth triangles. Okay, so growth triangles on C are getting bigger than B. And what I mean by that is these plus numbers are getting bigger. I'm up here at plus 384, but over here I'm nowhere near that size increase. So the increase on sequence C is going to continue. The triangles are going to continue to get taller and taller and taller. How do the growth triangles on sequence B compare to the exponential growth of growth triangles on sequence C? They are not as tall. All right. So I think that's everything there. I don't want to say it's a mini unit, but it's sort of an in-between lesson on getting ready for the next lesson. So shouldn't be too much. You shouldn't be feeling there's too much new material that you're mastering in this lesson, more like introducing. All right. See you in class.